Welcome, I am Amos Olaleka Kemi by name. I'll be speaking on atomic theory according to quantum mechanics, which is an inorganic approach. At first, I want to thank Professor Dr. Gian Marcel Haugallo for giving me this wonderful opportunity to explore and dig deep more on this topic. Thank you. Yeah, does atomic theory simply implies? Atomic theory is a scientific theory which states that all matter is made up of extremely small particles called atom. And what does this atom itself means? An atom is the smallest particle that still has the same properties. And some people will say an atom is the smallest indivisible part of an element. They are right with that. And before exploring much on the topic atomic theories according to quantum mechanics, I want us to go together by starting from the foundation. Where does the name atomic theory arrive from? And why am I here speaking on atomic theories? That means there are some scientists that has played an Herculean task by what? Arriving at this atomic theory name. And I would like us to walk together to the years back. I think we are going, wonderful, we arrived there. Historical development of atomic theory. Before the term atomic theory was sanctioned in the scientific community, there are some people that have played a great quota, that is, they've contributed a great quota to the scientific community. And my first 5 slides will be talking about the historical development of atomic theory, where I will just paraphrase the first 5 slides. At first, picture of Democritus from 460 BC to 370 BC. He was the one that arrived by saying that matter ultimately consists of discrete particles which are termed atomos. Now we know where the term atom comes from a Greek word which simply implies indivisible or uncuttable. Remember, Democritus is a Greek philosopher. When he said that, Aristotle and Plato, which had they tend to go against his idea, though Aristotle now said that matter is made up of 4 elements, where it terms earth, water, fire, and wind. And after a long break, John Dalton came out with his wonderful idea, which we now embrace today, which is atomic theory. Now we understand what I'm saying now, that atomic theory was given to by John Dalton. That is, it was the one that gave the name atomic theory. So he assumed that elements consist of tiny particles called atoms. That's his assumption. So he gave 3 postulates in which we are using in the modern atomic theory. That's an element is composed of extremely small particles called atoms. He gave law of conservation of mass. He explained more on that. He also gave law of constant composition. And note something, when he was talking about the 3rd postulate, that is law of constant postulation, he was able to arrive at the basic quantitative law of chemistry termed law of multiple proportion. Okay, I didn't state that. The law of multiple proportion states that when 2 elements combine to form more than one compound, the mass of one element which combine with a fixed mass of other elements are in a ratio of small whole number. Okay, and now progressing, John Dalton received award. Yes, he received award, a Nobel Award for atomic theory, which he discovered. And remember, he faced a lot of challenges from the philosophers and before it was accepted into the scientific world. Now let me quickly divert. Now that atomic theory was accepted in the scientific world, it's just like when car was created, was invented rather, back then. Can we say that those cars that was invented is the one we are still using till today? Yes, we are using it till today, but there are some advancements that have been made. Back then, cars are using key. Nowadays, we can see Chevrolet, Fiat, Rolls-Royce, some sophisticated car that are keyless now. That is, they don't use key, unlike before they are using 504. But now, so that's what is happening in the scientific world as well. When atomic theory was discovered, there are some advancements that has been made, and without wasting much time, the first advancement that was made was done by Joseph John Thomson. He discovered the electron, where he called chocolate chips model. So he's a British scientist, and this is pictorial illustration. The first thing he did was that he used a glass tube and coupled with positive and negative charges. So what he discovered is that the light was attracted by positive charge and negative charge tends to move away. So he now gave that, oh, the negative charges that are diverted, these negative charges particles that Thomson discovered is what he now called the electrons. So without wasting much time, remember John Thomson, J.J. Thomson, as a student, though he's a former student of his name is Ernest Rutherford in 1991. This is a pictorial illustration. He now said, oh, what my teacher did, let me explore more on that. So when he explored more on that, just to carry out his chocolate chips cream theory, then he discovered nucleus. That's why we call him father of nucleus, without wasting much time. Another student of his, I think J.J. Thomson's students are very brilliant. So thanks to expand on what Rutherford nuclear discovered, that is the father of nucleus discovered. The name of the man is Niels Bohr, 1930. Sorry, there's no pictorial illustration for that. He stated that electron orbits the nucleus at a fixed energy. So he said when there's nucleus at the center, the electron moved at a fixed energy and a distance. But look at what now happened. When Heisenberg now said, no, it's not possible. Now showing it is possible to determine the exact, it's not possible to determine the exact location of an electron, which he now termed uncertainty principle. So that is what gave rise to where I'll be speaking on. That is my topic, atomic theory according to quantum mechanics. So now the idea that electron cannot be precise gave rise to the quantum model of the atom. We are trying to find the location of the electron. Now progressing to the chance of finding the exact location of an electron in the nucleus. Okay, they said we can't find the location of the electron. How can we do that? Now, quantum mechanics. So there's what we call quantum mechanical model of atom. So it states that electrons are not in a circular orbital around the nucleus. Yes, okay, you said it's not in a circular orbital around the nucleus. Electron are in three-dimensional region around the nucleus. They now said, oh, it's in a three-dimensional region around the nucleus called what? Atomic orbitals. What do I mean by these atomic orbitals? That is this atomic orbital that describe the probable location of the electron that we have been looking for? Oh, wonderful. Who now give rise to this quantum mechanical model of atom mentioned in slide 6? Who gave rise to that? So look at what it is. Erwin Schrödinger that gave rise to that. But before that, it was with this Broglie that proposed that electron behave like wave and particle properties at the same time. Before this, Erwin Schrödinger now made a bold move by refining the wave particle theory. So now note, Erwin Schrödinger proposed the quantum mechanical model of atom, which treats electron as a matter wave. Note my statement, it treats electron as a matter wave. So look at what Erwin Schrödinger gave rise to an equation in which we can see in my slide. So whereby he said H is the Hamiltonian. So look at the Erwin Schrödinger complicated equation. So it's shown in this. It's more of mathematical and physics. So we can still explore more on that. So Erwin Schrödinger complicated equation gave rise to a new epoch in chemistry. This new approach is now called quantum mechanism. Sorry for that. Therefore, quantum mechanical model of atom determines the energy of an electron. It determines the energy an electron can have and how likely it is to find the electron around the nucleus. Look at a pictorial illustration. This is the nucleus at the center. This is the electron cloud. So the bone of contention is that we are trying to find the location of the electron. And never forget that nucleus is made up of proton and neutron. So how can we find this is where the electron is located, this is where the electron is located, this is where the electron is located? How? Now recall from what I said. I said since atomic orbital describe the probable location of electron, we then dig deep into the atomic orbital and say, okay, now what is the meaning of atomic orbital? They have been shouting that this man used a lot of equations to determine. Now let's explore more on that. Atomic orbital. An atomic orbital is often thought of as a region or space in which there is a high probability of finding an electron. I think I said that earlier. So there are 4 categories of atomic orbital. They include the SPDF. Look at the pictorial illustration. We have the S, which is a circular shape. We have the D, which is the dumbbell shape, and we have the sorry, we have the P, which is the dumbbell shape, we have the D, and we have the F. And now let's progress again. So numbers and kind of atomic orbital depend on the energy sublevel. Wonderful. The lowest sublevel is XS. Second is sublevel is P. The third sublevel is D, while the fourth sublevel is F. We can see from the pictorial illustration, I think I tried to incorporate lots so we can understand. So the number of orbitals in the sublevel is 1. Whenever you hear S, the orbital is 1. And and note something, every orbital can hold up to 2 electrons. Look at the first orbital, which is S, which is 1, can hold 2. But remember, every orbital can hold up to 2 electrons. Look at S, the P it's what? The sublevel is 3. It can hold 6 electrons. While the D, which is 5, can hold 10 electrons. While the F, which is 7, can hold 14 electrons. I think the total possible occupying electron is what we now calculated here. The 2, the 8, the 18, and the 32. So, and when we are going on, we tend to understand much more on that. No, at this point, the big question is, how does quantum mechanical model describe the probable location of electron in an atom? How and how? I think I never answered that. They talked about atomic orbital showing us the location. Now we've understand atomic orbital, we've noticed that it's been divided into various types of sublevel. We have the SPDF, and we now understand that in the S sublevel, this one has 1, this one has 3, that is the number of orbital is 3, while the number of orbital of D is 5. Let's take a little step back. 1 orbital, 3 orbital, 5 orbital, 7 orbital. I think I'm making sense now. And here is what I illustrated. Now we're now trying to understand that in the S orbital it can occupy 2 electrons. In the P orbital it can occupy 6, but the total will be 8 because we are going to calculate the S and the P together. In the D orbital it's what? 10. But when we want to calculate the total electron there, it's 18. Now while in the F orbital it is 14, but when we are calculating the total it is 32. Now we are still looking for the location. That is when my question pops in again. To answer that is when quantum number enters again. The quantum mechanical model describes the probable location of electron in atoms by describing the characteristics of electron and their orbitals via 4 numbers called quantum numbers. So this quantum number, the 4, 1, 2, 3, 4, are the one that now gave us the answer to the location. Where we can find the electron. Without wasting much time, I'm going to talk about principal quantum number. That is the principal energy. At first, principal quantum number, it's symbolized by N. That is, the principal quantum number describes the average distance of an orbital from nucleus and the main energy level of electron in an atom. Look at from the pictorial illustration. It tells us that how far is the electron from the nucleus, and the symbol for that is N. N is equal to 1, N is equal to 2, N is equal to 3. And we can see now, look at the first nucleus. I think I explained much on this, and I said earlier that on my slide 10, if I'm right, that why am I mistaking S and S? S contains maximum of 2 electrons. We can see it here. We can see this, the total electron. So this is the SPD. So the far that the electron, the greater the energy. We can see the electron rather. So now let's progress. I think I can answer that. Remember, it's symbolized by N. And now number 2, the angular momentum quantum number. It is symbolized by L. And look at one funny thing. The number describes the shape of the orbital. This one just describes the shape of the orbital, while the initial one I explained tells us the average distance, how far they are. And for us to get L, the shape is limited by principal quantum number. N will be the one to tell us L. So that is, the value of L is dependent on N. Look at the L shape that I said, circular, P is dumbbell, D and F. So each main shell is subdivided into subshell Am I making sense? That is, the orbiter has the same value of n, but different value of L are called subshell. I think I incorporated something. So please note the difference between shell and subshell. So the angular momentum quantum number can have positive integer value from 0 to n minus 1. So now, how can we know the subshell of L? So the different subshell are denoted by the letters. Look at the S. The S has 0. That's for L. And for P, we have the SPDF. When N is 2, that is SPDF. When P is 1, L will be 1 rather, sorry. When S is 0, when there's S, L will be 0. I think I got myself right now. When P is there, L will be 1. When D, L will be 2. And when it is F, L will be 3. And when it is G, L will be 4. We can see much on this. I think we are going to understand better. It looks abstract now. Let's see what I'm saying. Yeah, the relationship between L and N. So for us to look for L, N will tell us how to look for L. So when N is 1, L will be 0. Using the formula, incorporating 1 here, 1 minus 1, that's 0. That means X will be the next one. And when N is 2, 2 minus 1, that means 1. That's 0 and 1. So it will have the S and the P orbital. So when N is 3, L will be what? 0, 1, and 2. So that will be 3 minus 1. That will be 2. We are having it here. So L will now be 0, 1, 2. So it will now occupy the SPDF shell. And when N is 4, 4 minus 1, that's 3. That will be 0, 1, 2, 3. So it will now occupy the SPDF shell. So we can see much on this side. So we have the 1S, we have the 2S, we can see. We have the 2P, we can see here. We have the 3S, 3P, 3D. That's, look at them, 3S, 3P, 3D. We have 4, 4S, 4P, 4D, and 4F. 4S, 4P, 4D, and 4F. So if you want to arrange the electron configuration, we are still going to go to the place. So I think I'm making sense with this. So that's the relationship between N and L. Without N, we can't find L, and that's the formula for finding N. And now progressing to the magnetic quantum number orbital in each subcell, symbolized by ML. Magnetic quantum describe how the various orbitals are oriented in the space, and it is denoted or symbolized by ML. So that is for us to find the ML. So the function of this ML is just to tell us how the orbitals are oriented in the space. So, and it depends on the value of L. So that means when we get L, issue has been resolved. ML has been gotten. So, and the value allows a integer from minus L to 0 and to plus L. So this is the formula without wasting much time. Below shows the LS orbital. We can see this L is equal to 0, ML is equal to 0. When L is equal to 0, that means ML is equal to 0. So this is the shape. I incorporated that. And now look at, if the value of L is 1, which will now occupy the P orbital that I said earlier. So that means ML will be what? Like I said from initially, that will be minus L to what? Plus L. So we will now notice that so far L is 1, that means ML will now be what? Minus 1, 0, plus 1. That means there are 3 different P subshell for the particular orbital. We can see it here. ML is equal to minus 1. So it can occupy the x-axis, the y-axis, and the z-axis. That is 3 shapes. And if L is equal to 2 as well, it occupies the d orbital. So we have 5 value of M: minus 2, minus 1, 0, 1, and plus 2. You can see it. ML is what? Minus 2 plus 1. So that is the orientation of the orbital. Now trying to explain the spin quantum number. Talking about the spin quantum number, that's Stern-Gerlach experiment. So that's the scientist that carried out the experiment arriving at this. It is symbolized by MS. And the only bone of contention here is just that only two values are allowed. We have the plus 0.5, that is 1/2, or minus 1/2, which is 0.5 as well. For each subset, there can only be two electrons, one with a spin of plus 1/2 and another with a spin of minus 1/2. So they spin in opposite direction. So look at this. The spin quantum number describes the direction of electron in a magnetic field, either clockwise or anti-clockwise. I illustrated it here. Electron going up is what? Plus 1/2. Please note this. 1/2. Electron going down is minus 1/2. So this is a pictorial illustration again. You can see it's going down, going up. So now, summary of all what I said now is N represents the energy level, L represents the sub-level, ML represents the orbital, MS represents the electron spin. Now, how do we identify the quantum number of an electron? That is when we tend to understand more. So, how do we identify the quantum number? For identifying quantum number for 3p5 electron, let's progress. Look at 3p5. At first, n is equal to 3. How do I know that n is equal to 3? This is 3. N is equal to 3. And this p is going to illustrate. Yeah, p will tell us the value of L, which is 1. How do I know p is 1? Like what I said when we have s rather, that means p will be what? 0. When we have p, I think I'm making a mistake. Sorry. When we have s, L will be 0. When we have p, L will be 1. When we have d, L will be 2. When we have f, L will be 3. So I think I explained that in slide 10 as well. So remember that p has 3 orbitals. Yes, wonderful. Let's represent the orbital by dash dash dash. We represented that. Now L is 1. So far I told you that when L is 1, it will give us the location of ML. That is what ML implies from what I explained earlier. So that means ML will be minus 1, 0, and plus 1. So putting it under the 3 orbitals of p, that's minus 1, 0, and plus 1. So focusing on the 5th electron, yes, we want to know the location of the electron. You know, that is the main purpose of this presentation. So we want to know the location of the electron. At first, using the Bond's principle, the first one is 1. The first electron is on minus 1, second electron on 0, third electron on 1, another electron facing down, which is the 4th one, and the 5th one is facing down. So we've known the location of the electron now. So the 5th electron landed on the middle orbital, which means that what? Where ML is equal to 0. So that means the electron is on 0. That is ML is equal to 0. Now we want to know MS. What is MS? I told you that MS is either plus half or minus half. That is plus 0.5 or minus 0.5. Now, so far the 5th electron is facing down. I think that one is self-explanatory. That means it is minus 1/2 because the arrow is pointing down. So now, the quantum number, I think I answered that. N is equal to 3. Yes. L is equal to 1. Yes. MS is equal to minus 1/2. Yes. And ML is equal to 0. Yes. So they are the number that correspond to 3p5 electrons. I think I answered, and we've known the location of electron. Now you can find the location. Now the next example, let's do for D, the 4d5 electron, using the same approach I used on slide 20. At first, N is equal to 4. Yes, this is 4. And D, like I explained here earlier, I said when it is S, that means L is equal to 0. When it is P, that means L is equal to 1. When it is D, that means L is equal to 2. And when it is F, that means L is equal to 3. So please, that means so far we're having D now. L will be 2. Wonderful. D will tell us the value of L. Yes, this is D. So L, which is 2. Remember that. And D has 5 orbitals. Yes, I explained that in the other slide. If you have 1, 2, 3, 4, 5. Now that L is equal to 2, what is the next thing? ML. ML will be what? Minus 2, minus 1, 0, plus 1, plus 2. Now putting it under the 5 orbitals that we got, focusing on the 5th orbital. Now, electron, we want to focus on this electron, 4d5. 5. The first one will be 1, 2, 3, 4, 5. So we can see that our Ml will be +2. Yes, because the 5th electron landed on +2, and for us to find Ms plus, that will be what? +1/2, because what? It is facing up, because the 5th electron is pointing upward. So below shows the quantum's number. N is equal to 4, L is equal to 2, Ml is equal to +2, Ms is equal to what? +1/2. Now the next example, using chlorine. Remember, before opting into the next example, the S block on the periodic table, this is the S block, this is the D block, this is the P block, and this is the F block. Now chlorine has 17 electrons. We want to know the location of the electron, abi? Now, so far chlorine has 17 electrons, and I explained earlier how we can arrange the electron configuration. If you are finding, if there's more light, it's on slide 10. So I explained. Now 1s, 2s, 2p, 3s, 3p, and 4s. Chlorine has 17 electrons. Let's distribute it according to their habitat. This can contain 2, 2, 6, 2, and 5. So the last electron added on 3p orbital, which is 3p5. So we'll be concentrating on 3p5. And I said earlier 3, which is n. So p will tell us, I told you that when it is p, that means L is 1. And now when L is 1, we've gotten Ml plus, we've gotten Ml solution. That will be -1, 0, +1. And for us to find the location of Ms, we arrange our electron, that is our 5 electron, like I did initially. So let's take a preview back. I did initially, yeah, this is it. I did initially on slide 20. Oh, I think we can check that one later. I did that initially on slide 20. So that's when we get our answer. So now, if they are finding it difficult for the arrangement of the configuration, 1s first, followed by 2s, followed by 2p, followed by 3s, followed by 3p, followed by 4s. That's how it progresses. Now, I think, yeah, this is how to remember. 1s first, 2s. Now, look at the next example using manganese. Manganese has a 25 electron. At first, I want to distribute it. I'm going to take it 1s2, 2s2, 2p. Yeah, I'll start from this. 2p, 6p, and 3s2, 3p, 6, 4s2, and 3d5. So the last electron added to the 3d orbital. So I'm going to bring this one out. 3, that means n is equal to 3. L is equal to 2. How did I know that? DL orbitals is telling me that whenever it is D, it is 2. Remember that. Whenever it is D, L is equal to 2. Whenever it is F, L is equal to 3. And ML is equal to -2. How did I arrive at that? L will tell us how ML will arrive at its answer. And MS is equal to +2 or -2. If we dig deep, then we are going to differentiate if it's going to be plus or -2. I think with this I'm able to explain the term atomic theory according to quantum mechanics, which is an inorganic approach. At first, I try to start from the foundation by us understanding the term atomic theory, and after that I try to explain to us how advancement was made, and after that I try to tell us the bone of contention, that is to find the location of electron. And then they use various quantum mechanics approach, in which quantum number tends to be the one to tell us the final solution. Thanks very much. Thank you very much.